Hi everyone, welcome to today's webinar. My name is Erin. I'm one of your resident webinar hosts here at Software. Here, I'll flip my camera on just to say hello to everybody. Hi. So today's plan, we are going to be talking about terrain modeling. And terrain modeling really is an essential first step in any type of project in our software, whether that is a road design, a site design. Having a terrain model is really the foundation, that essential first step that you need to take. So in today's webinar, we're going to talk a little bit about how to create a terrain model from a whole bunch of typical data sources, as well as some strategies and suggestions to help you allow them to have good performance in your computer and to help it make it a little bit easier. So with that, we're going to get into a little bit of content to begin with some concepts, and then we're going to be passing it back and forth over to Matthew Dickey, our other resident webinar host here at Software, for some in-software demonstrations. Okay, to get started, the first sort of concept, terrain models are actually a TIN model for us. And a TIN is a triangular irregular network. It takes all of these known data points and it connects them with triangles. And the result of that, you can see here in this other visual that's coming from total station data, and you can see how those triangles are connecting all the known data points. And the quality of your surface is really dependent on the distance between those known data points. So what are the inputs that you can use to get to a TIN model or a terrain model? So today we're going to talk a little bit about a couple different types of high resolution data, including LiDAR, drone data, as well as DEM data. We're also going to talk about conventional data, in this case total station, and how you can import that and some tips and tricks for it. There are a few other types of data that you can input into the software, but we're going to skip today just in the essence of time. For example, if you're bringing your data in from a DWG or a DXF format, so bringing it in from another piece of software, we're going to talk about that one possibly in another future webinar or as a video. So stay tuned to our YouTube for that one. And then the last type is land XML, and again, we're not going to be covering that in today's webinar. Okay, so before we get into some actual examples, I really wanted to cover off one large concept. And that first concept is really all about contours. So contours are something that we can calculate at the same time that we calculate that TIN surface. Now, contours, when we add them to the model, they actually don't represent, or I should say, they're not changing or modifying the surface. They're really just adding visual data. They're a visual aid for you as a designer or an engineer. And the contours, if they get to be more dense, they're actually not changing our surface. They're not improving the quality of our data. They're just adding points. And so there's a few different tools that we have in the software to help you work and manage your contours and some suggestions. So the first one of those is just an awareness that contours themselves, and I highlighted one here just to show you, they add points to your model. So this particular contour, it's adding 67 points to the model. Now, this is a really small model, but you can imagine as you get into some of the high resolution large data sets, contours can actually add a tremendous amount of additional information to your model without actually improving or changing your surface. So we have some tools in order to help you control the number of points that are inside of contours. And this can help your model run faster, and be a little bit more dynamic. So one of those methods, and this one is actually to add points, is called contour smoothing. So smoothing is going to take your contour and it's going to add additional points in it to smooth it out. So our original contour, and we're going to keep looking at that same contour right here. Before it was 67 points. And then after you use something like smoothing on that contour, we're actually increasing the number of points on it. And you'll notice that it's not quite so jaggedy. So if you're looking to get smoother looking contours, you can add points to your model. Again, not usually suggested, especially when you get into those big data sets, but you've got this ability to add smoothing. The one that we want you to focus on a little bit more is thinning. So thinning contours can actually help reduce the number of points. Again, focusing on that same contour, it was originally 67. When we smoothed it, we went up to 190 points. And with thinning, we're able to actually reduce points. And in this example, with the tolerance I've set, we've gone down to 28 points. So contour thinning is actually a really useful tip that you can implement when you go and create your TIN models. And if you're not wanting to make your models that much slower, using thinning is really, really helpful. And I just wanted to sort of re-emphasize before we pass it over to Matt here for our first little in-software demonstration, that contours themselves can actually act like a really large data set too. So dense contours, they take a lot of time to draw. They can take up memory, they increase your file size, and really they're for visualization. So we have 3 suggestions that we hopefully, if you're working with large data sets, can implement to help keep your contours under control. The first of which is using that thinning tool we just talked about to reduce your point count, including the elevation labels only in the final output, and saving those contours to an external file to have it as a background display, almost like what we would do in OrthoImage. So with that, I'm going to flip the presenter over to Matt. And while I do that, I just want to say a couple pieces of housekeeping. You are all muted. That means that we don't want, still keep asking questions. I just get to type them and we'll address those as we go through. Yes, and this video is going to be up on YouTube, so you can ask us questions there too. And with that, my camera's off. Matt.
All right, I will do some clicking around in the software. So to start, the same example that Erin was looking at, we'll just kind of talk about the things she was talking about with the software open. So I've got my surface, we can see it. We've got our actual data that's used to create that surface. I've got some contours being drawn here. And yeah, just to reiterate what Erin was saying, the contours don't actually affect the surface that we're working with. So we can remove those contours and we could still do our design. The volumes in our design would be the same. Yeah, it's just the contours help add a little context for what our topography is doing if we're just looking at it in the plan view. Now I'm going to regenerate my contours. I've got my intervals set, in this case 5 and 1. If they were really far apart, again, still the same surface. If they were much closer together, still the same surface. To start, I've got my thinning and smoothing turned off here. And we can see with that, let's go over here. So this contour, so that's selected feature, one feature selected, 67 points in it. The contour is perfectly tracking our surface. Now, smoothing contours is kind of nice where you have sparse data and you might say, well, the actual ground that I'm intending to model isn't a series of triangles and we want to just smooth that out for visualization. And that's where smoothing comes in. But when we do that smoothing, I'm going to go with 20 cents here. And let's just we can see, well, we're smoothing around those edges that were once there, and now we're up to 187 points. So we can see that selected feature point count down there. So yeah, it's a tool for visualization. We can see now it's not perfectly following that surface. It is smoothing it out for the contour. Now, if we wanted to, we could do our thinning here. It's the same thinning tool that we have over here. And if I just tell this, well, let's simplify this down. So thin it based off of 20 centimeter tolerance. Well, we've dropped the number of points in that down to 94. I'm going to just hit undo. So 187. I'm going to turn my symbols on so we can actually see this. We can see all those points. We'll do that simplification. And let's That was probably a little more apparent over here. So here we can see those points. And really all it's doing is it's getting rid of redundant points that cause a distance difference less than 0.2. So we can see those collinear points are removed. And as Aaron said, it's really, the thinning tool is really there to help keep things light and get us well, contours that are not heavy, take a long time to draw, and really weigh down our model. Yeah, and usually you can just run with the default settings and get something that the difference between what you're seeing and the thinned and unthinned is negligible, but it does make a difference in the model. And just another thing to mention here, this is really small, this file, so it's not much of a difference on this one, but if it was a really large data set from LiDAR or something similar, then that's where we want to start being aware of well, number of points and how heavy we're making things. So with that, I'll hand it back to Aaron.
Awesome, thanks, Matt. So now the format sort of for the rest of the webinar, we're going to go through a whole bunch of examples. We're going to show you how to import them, and we're going to talk about some really key suggestions as we do so. So the first type of data we're going to actually focus on is drone data. And with this, we're going to really try to illustrate the concept of strategic thinning. So RoadEng and Terrain Tools includes functions to allow you to control the point density of your data. This could be to a corridor, to a polygon, all of the data as a whole. And as you can see here in this graphic we've got up on the screen, this particular data set has been strategically thinned to an area of interest. The area of interest has been kept at full resolution, and all the data outside of it has been thinned to be quite a bit more sparse. Now, this data set, again, isn't a huge data set. I think the original one was only at about 2.6 million points. But as data sets get larger, and we're seeing, you know, obviously absolutely massive data sets, 100 million plus points, those need thinning. So this type of tool has a huge importance, I should say growing importance, as the data set size increases. That being said, for our typical spec'd out computer, we recommend keeping your modeled points less than 10 million. And if you have an opportunity to apply strategic thinning to stuff that you're not going to use, we absolutely recommend it because it keeps your model moving really light, really dynamically, and really fast. So in this example, we're actually going to talk a little bit about drone data and how it's been oversampled and how you can apply thinning to it to help improve the speed of your model. And with that, we're going to go back to Matt for our next example.
Cool. So this one, I'm going to just open up an entirely new terrain file, and we are going to bring in our drone data. So this data, and we'll see it as we bring it in, it is very, very dense. So it's kind of, if you were compared to the resolution on a TV, well, if you're watching the hockey game, do you really need your image resolution so dense that you can see the eyelashes on the players? That can affect your ability to appreciate the game. Probably not, and you're probably going to need some really special hardware in order to do that. So we are going to bring in this drone data. So we've got an LAS file here, and usually when we're working with LAS data, if it's coming from classified LiDAR data, we'll just run with ground points. Now, one thing that's fairly common for drone data is for folks to work with unclassified data sets. And that's a lot of the time when that data is being brought in while it's surveying something like a pit or an open site where there's not a lot of trees that make it so you require classification. So for this, if we just brought in the ground points, well, we'd get nothing. If we hit examine files, we'll let this think for a moment, and really what it is none of the points have been classified. So we'll just bring in the never classified points. We can watch as it reads those points in. And we've got this big magenta blob in the middle here. And we can see down here, we've got 31 million points. Now, I'm going to zoom in here so we can see this a bit better. So we can see those points, they're kind of irregularly spaced, but I'm going to just click my measure tool and I'm going to arbitrarily measure around here. So that one's about 10 centimeters away. That one's less than 10 centimeters away. So we've got a very, very dense data set. And as Aaron introduced, well, if 10 million modeled points is a good rule of thumb, this one's going to be probably pretty sluggish if we model it. So we're going to thin it. And in this case, we don't need to identify we want to keep the full resolution in this area or not. The whole thing is so dense that we can reduce the resolution for all of it after that's been imported. I've clicked off to the side to deselect those points. I'll go over to terrain modeling. I'll click simplify. And here we have a few different options for how we thin our data. And if we wanted to, well, keep a little polygon here with the full resolution, we could add an excluded region. But as I said, I want to thin this whole thing. I'm going to set my spacing here. So with that, I'm using the basic grid simplification. So here we've draped a grid over it and it's making sure within each one of those 0.5 meter cells, we're leaving at least 1 point. So the other ones are similar. We can tell it to maintain a distance between the points within cells, and we've got a 3D option to do that as well. But we'll keep it simple with the basic grid simplification. We're going to go from 31 million. We'll hit OK. We'll hit OK. And so we've gone from 31 million to 360,000. Now, when we want to model that surface, we can quickly click model. And we can see what we're dealing with. And there we are. So we've got a much, much more manageable file size, and we're still keeping our points within a half meter grid spacing. So that's a strategy for dealing with drone data, oversampled drone data, and sending it back to Aaron.
Excellent. So our next concept that we're going to talk about is this idea of swapping out your TIN model. So having a TIN model that is, or I should say a terrain model that is lower resolution, and then swapping that for one that is higher resolution. And here, just to kind of show you the idea of this and talk about where you might want to apply it. So for example, with a greenfield project, you're not sure where to put your alignment or your site design, bring in all the data at a lower resolution, figure out where your project needs to go, and then define that area of interest, and then swap your terrain model to have that full resolution data set, but just for your area of interest. So for this example, we're going to take a look at a LiDAR data set and show you kind of how you can, begin with a lower resolution, change that model out, and include it at higher resolution. And I don't think Matt's going to cover this part in our actual webinar today, but you can also do this same swapping of the model out at the road design phase. So you can actually change the TIN that you're using for a road design project to be higher resolution. So if you'd go and get something at the preliminary stage, get some rough costs, rough actual geometric design from it, you can still swap your model out. So this is a concept of swapping TIN models. We're going to use LiDAR as our example for this one. We'll show you how to import it, and then we'll talk about the concept. So Matt, it's coming back to you.
All right, perfect. And I will show it. I'm not going to do the preliminary design, but I'll show the concept behind swapping that out. All right, and So with this, I am going to cheat a bit there to really show it. We're going to use a big data set, so I'm not going to wait for it to get read in, but I will start from the 0.0 here. So I'm going to click Insert File, and I'm going to bring in my LiDAR tiles. I'm going to hit OK. Now here, these LiDAR tiles are classified, so and as we do most of the time, we want to bring in our ground points, get our projection assigned. If we knew that, well, within a polygon or within the distance of a corridor, we could do our selection right from the get-go, but we're going to imagine it as though we don't know where we want to put that road. We have no idea beyond we want it to be on this surface. So we'll pretend that I hit OK here, and it'll just save watching my computer think for a few seconds. But after we hit OK, we get all our LiDAR data brought in. We can see that LiDAR data is being drawn, so I don't have to wait for it. I'm going to hit Escape. And so we've got this big magenta blob, and I can see I've got 46 million points in my model. So kind of like we did last time, well, we're going to reduce the resolution, and we're going to reduce the resolution just so we can go through, get a preliminary design, and then we'll crank up that resolution to deal with the full data set as we go to finalize that design. So in here again, we'll go simplify. I'm going to use the a 10-meter grid for this. But you can see I've really cranked down that resolution. If I hit Control A, we can see the points that we're dealing with. I'll click Generate. I'll generate my model with some contours here. And there we are. So we still have our surface for that whole area. It's just that we don't have all the gory details. I'm going to hit File, Save As, and I'm going to save this as 10-meter topo. And here I'm going to pretend a little bit, and we'll pretend that I've set up my location file, and we've got our initial design based off that surface, and we're ready to move on to the next step. So we'll just fire up location. We'll look at this kind of preliminary design that we have. We'll take that preliminary design, we'll export it out so we have a line, and we can thin our data down based off of a corridor. So there's our alignment. We probably want really high resolution data as we're close to the alignment, but outside of it, we might not care about it at all. So here I'm going to hit File, Save As. I can export that out in a number of formats. I'm going to just dump it out as a, which one will I go with? Sure, we'll go shape. I'll just get my plan points. Just want a center line. Great. Now I'm going to go back into terrain. I'm going to insert that shape file with my center line. So we've got this feature. Now we can bring in that LiDAR data. But instead of using a reduced resolution, we can say, well, I want my full resolution within 100 meters of that alignment. So total corridor width 200, 100 meters either side. Outside of that, we can click, oh, we want to skip all the points. And again, I'm going to cheat just so we don't watch that, bring in the LiDAR data the same we did on the drone example, but we'll end up with something that looks like this, where we don't have those tiles full of data, but within that 200 meter width, we have our full resolution. We can take that full resolution data, model it, we can take a peek. So we can see we've got a lot more detail in this model. We're down around 2.8 million points. We're gonna save this. And then back in this design, rather than working with that low res surface, we can just go up to our reference surfaces button. We see the topo surface identified here, and we can switch that back to whatever surface we'd like. So we've got that one that's called full res, which we've just saved. We'll hit OK. We've got a different projection in there, I guess. So it's going to recalculate. So we see we've got all those little undulations in our cross section now. We'll update our 3D display list so we can see that updated surface. And away we go. We can make any necessary adjustments to our design as we finish it up. So that is working with a high res and a low res surface. Again, you don't have to do this. If you have a good idea where you want your road to be, well, you can skip the low res portion and just send your data on import based off of a corridor. With that, I'll hand it back to Erin again.
Perfect. So kind of moving away from LiDAR, we're going to next take a look at DEM data. So DEM data is gridded data. So this is where it's being extrapolated from an original source, and now it is generated in a grid. And with DEM data, one of our big recommendations is to bring that data in grouped as features. And by grouping as features multiple points in each feature, we can actually save a lot of computer memory. The other huge recommendation we have with DEM data is to simplify it. So using what we call the Douglas-Pucher method, available through that simplify smooth option that Matt showed you earlier, we are able to actually remove unnecessary points. So a great example here, before the simplification, we have a uniform grid of data. But after, you can see that we actually are able to get all those elevation changes still captured in our surface, but drastically reducing the total number of points. So the flatter areas do not require as many points in order to have an accurate surface. And that simplify method is really wonderful at being able to highlight those. So in our next example, we're going to take a look at how to import DEM data and how to simplify it using that Simplify Smooth feature. So with that, we're going back to Matt.
Great. And all right, so just gonna open up terrain again. And we're going to click Insert File. We're going to grab that a DEM tile. So this one's fairly large, and for a lot of folks, or it seems a lot of folks will use DEM data interchangeably if it's high resolution enough with the LiDAR data. So this one is a 1 meter DEM. We'll click, oh, I clicked the wrong button. Look at me go. We'll click, well, a TIFF can be either DEM or an image. We want it to be a DEM. We're going to bring it in with just by clicking OK. And it's drawing those points. So as Aaron said, this is gridded data. And if we select just, well, one feature, we can see, well, each point isn't an individual feature. So this isn't just DEM that's behaving this way. Our LiDAR data, LIS data, is going to be grouped together with many points in a single feature. But this being gridded and on a straight line, we can use that simplify function to really, well, remove unnecessary points. So we preserve more points where the terrain's complex, and we remove points where it's planar. Now for this, I'm going to select all. So hit Control A. Not going to wait for it to draw. I'm going to hit Escape, and I'm going to come up here. I'm going to click that button here, and we're going to simplify it to be 0.1. So right now I've got 44 million points. So I'm going to remove all of the points that have a vertical difference from their neighbor of less than, from their neighbors of less than 0.1. So we'll hit OK. And it's going to think here for a moment. And as it's drawing here, we can see we don't have this solid wall of gridded points. We've got all the, well, the redundant points removed on those really planar slopes. We're going to model this. So we're going to go up here again, click Generate Model. I'm not going to create contours, just they're going to add clutter, make it harder to see what I'm going to show here in a moment. So we're down to 5.2 million points. So 44 million to 5.2 million. We'll click our little 3D view here. So I'm a sucker for the 3D view. So we can see we've got, well, pretty good representation of the ground still. And if I hit Control A, just so we can see all those points that aren't being displayed, well, we've got pretty dense data on those irregular slopes, but in the fields and elsewhere where we don't need that extra data to really visualize and model what's going on, we've got much sparser. So that's the simplified tool, the feature simplify tool used on DEM data. And we'll send it back to Aaron.
Awesome, thanks, Matt. Our next data type that we're going to talk about creating a terrain model from is conventional data. So here I'm referring to total station, but this can be applied to other types of conventional data as well, whether you're working with, say, an RTK. Yes, so for conventional data, we have two big fundamental strategies that we want to encourage you to use when you're importing and working with it. The first of those strategies is called an IOP, and this is an import specification. So if you have a very standardized way of collecting your data, we encourage you to use an IOP. So an IOP is a way of describing to the software basically how your data is structured and how to interpret it. Unlike those sort of high resolution large data sets where we just get a huge swath of data, conventional data is typically tagged with different point codes, and many of these different point codes define features that should be, for example, joined together, or perhaps we want to define those through different line work or symbology. And the example up here on the screen, for example, with the ditch point code, this is a feature that you'd want to have imported and connected as a polyline. We'd want to have a very specific symbol attached to it and a very specific color. And these are all things that we can define within an IOP file, the data structure and that sort of automatic joining of features and creation of polylines. And one of the examples I want to sort of highlight of how this can work is, on the left side, we've got an IOP where an IOP was not, sorry, we didn't use one. All the features were just imported as points. And you can see we've got a surface. But if you take a look at the roadway shape, that surface is not really indicative of actually what it looks like. So by including features as brake lines, so joining them, connecting them, and including them as line work and as something called a brake line, we're able to actually get a much clearer depiction of what our surface actually looks like by defining those brake lines on import. So Matt's going to talk about in a few minutes, bringing in that conventional data, setting up an IOP, showing you how you can save it and reuse it for all future imports that you've got, saving, quite a bit of time. The other piece with conventional data, and this is true as well with our high resolution data sets, but more so is this concept of leveraging the feature properties. So inside of the terrain module, you've got the feature properties panel, and the feature properties panel includes a list of different features that are available for every single point or feature themselves. These can include things that are defining its terrain modeling properties. For example, if it has elevations, so is it a 3D or a 2D feature? Its visual properties. Is it being displayed in the 3D window? Is it being displayed in the plan profile window? And then some different attributes. So different combinations of properties can allow a feature to appear very differently in your terrain model. And we'll just go back a slide here for a second. These features, these road edges, the ditches, and the center line are defined as brake lines. So those brake lines would have these same properties set. So they'd have brake line, they'd have modeled, which means to include in the actual model of the terrain, and they'd have elevations and connected set. And of course, the displayed. But by having different combinations of these properties, we're able to control the way that these different surveyed features appear inside of our terrain models. So these are the two concepts. We're going to now step into our last formal example of the webinar, which is importing some total station data. And we'll talk a little bit about using an IOP file, as well as using those feature properties to help create your terrain. And with that, the final pass back, going back to Matt.
So here I've got just some conventional survey data open in Notepad. So this is a CSV, pretty common format for folks to use. CSV basically interchangeable with text or ASCII data as well. This data, we can see we've got a series of commas. So we've got a number, coordinates, and a point code. So this one, I think, either total station or RTK data, common format for both. If we go up to terrain and we bring this in, well, we can make it easy or we can do it hard. So I'm going to click Insert File here. I'm going to go to my CSV. And if I were to just go with the default settings, one of the default settings is this ASCII text. So I can hit OK. I can see my Y coordinate is my second. So my northing, that's my third column. So third column here, separated by commas. this guy here, so my easting, and my point code is my fifth. So if that was formatted in a different way, we could switch these around. If I was using something other than a comma separated file, I could switch the delimitator. Big thing here though is codes. So right now, without my IOP set up, everything is just going to be brought in as the default spec. So if I bring this in, everything's going to come in as a point with a black cross, and it's going to be modeled. So I'll hit OK just to show it. So we can see we still have data, we still can model a surface from it, but if we want to create break lines and stuff like that and make it really easy to visualize and also use those break lines to control our surface, well, we'd be stuck playing connect the dots, which again isn't the end of the world, but we can go through, we can select those features, hit join, modify it, build it out. Now I'm gonna do something else here. So instead of that, we could go, well, I'm surveyed it a certain way. Let's create an IOP. So I've created a new format. I'll use this one as my starting point. We'll go in here. We'll set our options. So here I'm going to just do one of these, but I'll say anything that has a code that is CL. Well, I don't want it to be a point. I want it to be a line. I want that line to actually be a break line. I want my symbol at the surveyed point to be a triangle. I want it to be red. Oh, we can hit OK. If I want to use this in the future, I can save this as my default, or I can save it as another IOP file. But I'll hit OK. We can see the options here, and we can bring it in. So here, of course, I just did one code, but we can see our center line and it's connected for us. I'm going to just use one that is largely set up. So the same concepts just applied a few more times for these different codes. We'll bring it in and we can see all of our line work is connected for us. We've got symbols, that's special features like hubs and control points. We can go to our 3D view and we can model that just the same way as though it were the point cloud data that we were dealing with earlier. So that is using an IOP. The next thing to really talk about here is the idea of break lines, modeled points, connected points, etc. And I'm not going to do this in a ton of detail. Actually, I'm going to go back to that first data set we were using because it's a little simpler, a little bit less going on. So if I have, oops, I'm going to just remove my contours here so I don't end up clicking the wrong feature. But this feature here is called out as being a break line. So what the break line does is it is forcing our triangle edges to not cross that feature. If this wasn't a break line, I'm going to make it so we can see the points in this too. So if that wasn't a break line, so I've turned my break line property off, I've hit apply, and I remodel it. Now the triangle edges are allowed to cross that feature. So break lines are a tool to help you kind of draw your 3D surface in 3D and control where those triangles go. So I'm turning break line back on. I'll remodel my surface, and we can see that surface looks a lot nicer when that is modeled as a break line. Another important concept is the idea of modeled versus not modeled points. So I'm going to just draw in a point here. And sure, I'll go with an elevation of 100. I'm going to make this nice and visible, easy to see. So this point floating up here in space, since I've added it in, if I model our surface with that modeled, well, we've got this point floating up here in space. If we don't want that, if we want to keep the point, so have a record of it, and this one's extreme being so high above our model, but maybe we shot a sign or something, shot the actual top of the sign and want to know where that is, but we don't want it influencing our digital terrain model. Well, here we can turn off modeled. So we'll hit apply, we'll click generate. And we can see, well, here that point, since, well, it still exists, but modeled's not turning on. It's not included in our surface. And of course, we're showing it in the context of conventional survey data here, but even if you're working with LiDAR data and you bring in a feature and you turn model property on, maybe that feature was originally a 2D feature, well, you might get holes in your model going down to that feature that you actually don't want included in your model. So there it becomes important to just, oh, I don't want that to be modeled, select it, turn modeled off. And then the last thing worth mentioning here is connected. So this feature right now, we've got the points along it connected. And I'm going to remove my contours just so it's a little easier to see. But if we turn connected off, well, we can click it. We click that one point and we've still selected all 12 points associated with that feature. So that feature is still consisting of the 12 points it originally was. It's just that we're not drawing a line in between them. And going back to the DEM data that we were talking about grouping together and then LiDAR data. So for those, we don't want to draw a bunch of lines connecting those points. They are, well, grouped into features that are not connected by line work. Toggle that back on and see where they are. And with that, that's the gist of what I was hoping to cover today.
Awesome. Thanks, Matt. 2 minutes over. That's such a record for us. We're usually like 15. So thank you, everyone. 2 minutes late, but we're still going to hang out, answer a couple questions. So if you have a question, please type it into that question section of your GoToWebinar panel. All question askers do remain anonymous. And with that, Matt, there are a couple that have, built up here. So let's tackle a few of them. So the first question is for the contour labels. Aaron, me, mentioned adding them at the end. Why would you want to do that?
So contour labels, one, they usually take longer to draw than the actual contours. So here I'll just remodel it with the LiDAR data and I'll turn our labeling on. And it's going to take a moment. I guess I didn't have to redo the surface there. I could have just created the contours. But we can see those contours, and I guess I didn't have enough of them, but as we were panning around, they take a little longer to draw than the labels will take a little longer to draw than the contours. So that's one reason, just for computer performance. You can modify your terrain file right at the end and hit save, and it'll update in your design. The other thing worth mentioning with contours too is the spacing of them is going to be dependent on your scale. So if I'm going to zoom way in here, maybe not that far, but we'll zoom in quite a bit. So if I zoom in with a 500 scale, and I'll redo my contours, the spacing is going to be based off of, well, what's that going to show up on your plans with that scale set. So now we can see when we're at that 500 scale, it looks appropriate, but if we zoom way out, well, it's probably more labels than we'd like to see. So for that, just doing it later in the design process lets you figure out what kind of scale would you like to use and choose an appropriate scale when you actually set that label. So that's, I guess, a little trick.
Awesome. Okay, let's do a couple more. The next question, actually, that looks to be two kind of in the same space. So the first one says, my surface has triangles outside of my project. How can I correct that? And the other question that appears tied to it is, what is maximum triangle side length?
All right, yeah, those people must be talking to one another because they are definitely go hand in hand. I'm going to go back to this example here because it's a nice, easy one to manipulate and talk about. I'm going to just crank this up to include all. So if I include all, our maximum triangle length controls the maximum length our triangle edges can be. So if I go include all, well, basically any concave outline here is going to be filled in with contours, or sorry, with triangles. Now if we crank this down, so I've gone with 50, well, maybe I want a little bit more to fill that in. If I go too small, and this too small is going to be dependent on the density that your project was surveyed, how dense your surveyed points are, whether they're conventional points or LiDAR points. We see we don't fill in our surface where we'd like. So triangle length is one strategy for controlling the extents of your surface. Another way is by using tin boundary features. So here we could draw a feature around this and tell it, well, I want to include all the, only include triangles within that limit. I'm not going to draw them by hand. I'm going to just tell the software to use the current extents of our model to create that limit. I'm going to modify this. So here we can say, well, I want this to be a tin boundary feature. Hit apply. We'll go in here, we'll remodel this. And now if I hit include all, it's not going to make these really long interpolations. This tin boundary feature on the outside represents the outer limit of where I want that surface to exist. So there we are. That hems in what we're working with. So max triangle length is one way to control where your surface lands, and then tin boundary feature is another. And max triangle length really is exactly what the name suggests, and that is that it's the maximum length of your triangle edges while you're creating that tin surface.
Okay, last question of the day. This is, how do you make the points not display? And in this case, they're referring to a LiDAR file and they just want to be able to see the contours in plan view and not the points.
Okay. Let's just going to grab a tile. So on import, whether you're bringing in LAS, LAZ, or DEM data, there's an option to turn off display points right from the get-go. So this is usually a default setting. And with that, when we bring those in, I don't need to wait for all those to draw. I'll just select one group of them. When we bring those in, we can still see them initially. They're just that big magenta blob. The display property is turned off for them, so we don't have to wait for them to draw. And yeah, each individual point isn't adding really a lot of context for what we're looking at. Yeah, so we want the display property turned off for DEM, LiDAR data typically. When we do bring that in, they'll be selected. So to deselect them, we'll just click off to the side. And then the other thing here is if you've got a really large data set on that initial import, if you don't want to wait for those to draw, you can just hit escape on your keyboard and it's going to skip ahead and not draw every one of those features, but still give you an outline to show you kind of where things are at. And the last thing I will add in there, that display functionality, it's not just a LiDAR thing. If you want to include something in your model but not see it, well, we can turn off the display property for individual features here too, if you're working with conventional data.
And with that, thank you very much, Matt, for tackling today's webinar. Great examples. We hope that you guys learned an awful lot about terrain modeling, the different data sources that you can work with. If you have additional questions, please feel free to send them over to our team. You can reach the support group at support.team@softry.com. And we look forward to seeing you all at another upcoming webinar. Have an awesome rest of your day.
Thanks, everyone.